Hello, today we'll be walking through the ADC peripheral our team designed for ESCOM and demonstrating its capabilities through an application we built called the Analog Safecracker. The peripheral gives ESCOM access to analog voltage readings across multiple channels through a simple 3-register interface. Everything I show today is designed to highlight how that interface works and why we designed it the way we did. First, we'll do a quick overview of what our ADC peripheral does. As we said earlier, the peripheral sits on ESCOM's I/O bus and exposes 3 registers starting at the address of 0xC0. The first register is ADC data, which is at 0xC0 and is read-only. This is where ESCOM reads the result of the conversion from the ADC chip. This conversion result is a 12-bit unsigned value ranging from 0x000 to 0xFFF. Next, we have the ADC status register, which is at 0xC1. This is also a read-only register and gives the programmer visibility into what the hardware is doing. It has 3 meaningful fields: in progress, which is high while a conversion is, as the name suggests, in progress; channel select, which shows the currently selected channel; and fresh data, which tells us when a completed result is waiting to be read. The final register is the ADC control register at 0xC2 and is write-only. This is how ESCOM drives to the peripheral. The programmer sets ADC channel to choose which of the 8 analog inputs to sample, then it asserts start to trigger a conversion. The start clears itself automatically once the conversion begins, and this makes sure the user doesn't need to do anything but start and choose the channel. So what does actually using this peripheral look like from ESCOM's perspective? It comes down to 3 steps every time. First, ESCOM writes to the ADC control register using the out instruction. This sets the channel and then starts the conversion of the ADC chip. Second, ESCOM pulls the ADC status register in a loop, waiting for the fresh data to go high. That tells us that the hardware is finished and that the result is valid. Finally, ESCOM reads the ADC data register with the in instruction, which returns the 12-bit result and clears fresh data, so the next read is guaranteed to be fresh from a new conversion. We deliberately chose to only let the user choose the channel select and start bits to keep our interface simple. We use a constant single-ended unipolar mode, so all the user has to do is choose when to start and which channel to use. We also automated all the status bits, so all the user needs to do to check them is to look at the status register. To demonstrate all these features together, we built an application called the Analog Safecracker. The concept of this application is to crack a hidden code by using the potentiometer dials to guess the values and get closer to the goal with each guess. In the game, we select and track the channel to choose which voltage sample we are measuring by using the control and status registers. We make guesses based on the conversion value read by the ADC data register with the potentiometer dials. The closer we get, the more LEDs light up until both guesses are correct. We can change the goal by selecting the channel and doing a single-time voltage measuring conversion, which is now set to the goal. In this process, it also highlights the control register bits on the LED interface, so we can see what is happening with the fresh data and IP bits. Victory is achieved when all LEDs are lit up, and the voltage reads for both channels match the goal. Now let's go through the actual application and its interaction with the ADC peripheral. As we said earlier, we can select the channels using the control register and view them using the status register. Here we can see we're choosing the registers displayed on the Hex 1 display. We have a total of 8 registers, but we can see that currently only registers 0 and 1 are attached to the potentiometers, 0 to the left dial and 1 to the right. Now we can start the ADC conversion. Here we continuously track the value from the potentiometer and display it on the Hex 0 display. And as you can see, we turn the dial automatically. It displays, showing the repeating conversions from the ADC chip. When we make a guess by pressing the switch down, we can see the LEDs light up from how close we are to the goal. Now we keep guessing until we get closer and find the right value. Now that we got to the right value, we can show how our peripheral allows for multiple channels. We select channel 1 now, and we can see that we move the other dial to change the values on the display, indicating that channel 1 is now being measured instead of channel 0. Finally, we make guesses until the right answer, and the LEDs flash to indicate victory. Now we restart. If we don't want to use preset goals, we can set them here. We make it so when we set them, it shows the status register on the LEDs. We set the dial to all the way left and then lift the switch. The right LED is the fresh data and the left is the in progress bit. We make the in progress bit stay a little longer, since if we didn't, it would instantly flash off and it would be hard to detect. So this was a better visualization by just making it stay constant to indicate that it was lit up. Since we are channel 0, the 3 center are inactive. Now we can show that it still works by changing the channel by switching it to 1, and now we can see it is the same, but channel 1 is set to 1 on the status register. Finally, we can confirm that the goals are set by guessing our original values, which won't work, and now only the right values work. We can see we guessed values similar to the original preset goals, but it does not light up as many LEDs as it should. This indicates that the goals have been changed and that we have properly utilized the status register and control registers to change the goals. We finally choose the values that we have before all the way to the left and all the way to the right, and now we have a victory. Through our application, we have shown that our peripheral is working as intended. We can measure the potentiometer by doing repeated data register conversions and reads, and select the channel which properly changes which dial it reads. Finally, we can read the status register to see which channel and how the conversion is progressing. To summarize, the ADC peripheral gives ESCOMP a clean 3-step interface for reading analog voltages across up to 8 channels. The design prioritizes reliability and ease of use. The handshake is automatic, flags are self-managing, and channel selection persists, so that integrating this peripheral into a future project requires minimal overhead. As we saw in the demo, all of these features held up under real hardware conditions. The peripheral is ready to be used or dropped into any ESCOMP-based system that needs an analog input. Thank you.